In the next few videos, we'll look at how velocities transform in special relativity. We'll see that the velocity of an object is different in different inertial reference frames. Let's start by going back to classical physics and the Galilean transformations and think about velocity in that context. So let's say we have Anastasia, and Anastasia is moving left to right, maybe at 10 meters per second. And then Anastasia has a ball, and she throws the ball at a speed of 20 meters per second with respect to Anastasia. So Anna's moving at 10, she throws it at 20, meaning that it leaves her traveling 20 meters every second. So what would we see this at, you in the camera frame? Well, you would just see the velocities adding together. It's sort of, you're probably used to this from common sense without even writing down the Galilean transformations. Velocities just add together. If Anna's on a train at a certain speed, throws a ball at a certain speed, you on the ground see those two speeds together as just adding. In special relativity, though, it's not going to be so simple. And you can probably guess why. We know that time is different for observers in different reference frames, and spatial differences are different for observers in different reference frames. So it follows that velocities are going to be different for observers in different reference frames as well. So we'll start, as we often do, by looking at the situation using a two-observer diagram. So let's look at velocity transformations using a two-observer diagram. So I've started the diagram here. This is t and x. And let's imagine, as we often do, that the other observer, the moving frame, is moving at a speed of beta equals 3/5. And that's a convenient number because we've seen that when that's the case, gamma is 1.25 or 5/4. All right, so we'll start by drawing on the primed axes. Okay, so the time axis, it's going to be 3 and 5. And maybe I'll use a ruler for this, just to be a little more careful. All right, so there's my t prime axis. And then my x prime axis, that's going to have a slope of 5/3. It's going to be like that. Let's see if I can draw that. Beautiful. All right, so there's my x primed axis. So let's suppose that we have a object that's moving with a velocity of 3/5 in the primed frame. So let me take a second to draw that, and then we'll talk about it. Actually, before I draw that line, we should talk about calibrating these primed axes. Forgot about that step. All right. So remember how we calibrate things. Delta x is gamma delta x primed. So suppose I want to know like where delta x prime is 1. That would correspond to a delta x of 5/4. So I'm just, if delta x is 1, delta x times gamma is 5/4, or 1.25. So I claim that the x prime equals 1. It's going to be very roughly here. The idea is that this is about 1.25. And let's see, I also know that if x prime is 4, 4 times 5/4 is 5. So this 5 corresponds to a 4 there. And similarly, that's going to be 4. And then, let's see, this would be 2.5. 5. And if I go, it's going to be right about there. So 1, 2, 3, 4 in x primed, and 1, oh boy, 1, 3, okay. So 1, 2, 3, 4 in t primed, 1, 2, 3, 4 in x primed. So now I'm going to draw the world line of an object. All right, so let this green line be the world line of a moving object. Maybe it's Beowulf zipping by in a spaceship. And I claim that the speed of the green object, or Beowulf, whatever it is, in the primed frame is 3/5. Why do I think that? So let's say I want to do rise over run to figure out the slope. Or just look at, all right, so from here to here, how far has it gone in space, how far in time? So this point here has a coordinate of an x prime of 3 and a t prime of 5. So that tells me in t primed 5 seconds, it goes x primed 3 seconds. So let me write that, and I'll write that in blue, I guess. So v prime, what is that? Well, that's delta x prime over delta t prime. It's what our moving observer measures for delta x, and what our moving observer, the prime frame, measures for delta t. And so just to be clear, Beowulf is the object whose velocity we're measuring. Beowulf is not the blue primed observer. All right, so x prime, let's see, this green line travels a distance of 3. You can remember we go parallel to the t prime axis to get x prime. So this is going to be 3. T prime is 5. And so v prime, the speed as measured in the blue primed moving frame, is 3/5. So that's interesting because the moving frame is itself equal to 3/5, and that's just a numerical coincidence in this case. But notice that if Galileo was right, the unprimed at-rest observer would see something that's moving at a speed of 3/5 in a frame that's moving at 3/5, and would add those together and would say, aha, the speed is going to be 6/5, which of course is impossible because nothing can travel faster than the speed of light. All right, so lastly, let's measure the slope of this line in the unprimed frame. So I'll do that. I'm going to just choose a point. I'll choose this point. And I'm going to do rise over run for these 2 points, just reading right off this graph as usual. So this would be my unprimed velocity, or speed. And that's just the distance traveled by the green line in the time it takes. So let's see. Delta t is, I chose to be 5, just for convenience's sake. Delta x, it's less than 5. It looks to be about 4.5. So I'm just going right down here. This is 4, that's about 4.5. So 4.5 over 5, I think that's 0.9. Yep, should have been able to do that in my head. So again, Galileo would say the speed is going to be 6/5, 1.25. Oh, sorry, 1.2. But that's not what is actually happening according to relativity. Just reading off the graph, we see that we have a velocity like this. So let me just end by writing this conclusion in a sort of like what we've seen that 3/5, a velocity of 3/5 in a frame that's moving at 3/5 gives a velocity that's about 0.9. So velocities aren't adding together in any sort of normal way. That's why there are these scare quotes here. This isn't actually true, right? 3/5 plus 3/5 does not equal that. Okay, so in the next video, we'll derive a formula so that we can, the velocity transformation formula, so we can just plug into a formula and get more exact results. But before that, there's a quiz that will give you practice reading slopes of lines in multiple reference frames.